Hi, today we're going to just briefly talk about the relationship between heat transfer and thermodynamics. So, thermodynamics and heat transfer are complementary. They're related, but they're not the same. Thermodynamics tells us the total amount of energy exchange. We're looking at the endpoints of a process, not how fast the process occurs or how we can accomplish the process or what the process itself looks like. Heat transfer is designed to tell us about the mechanisms of the process of energy exchange and the rates, how quickly energy moves. So it tells us how and how fast. This gives us the details of the process, and because of that, it's very important for the design of power plants and heat exchangers and other systems. So thermodynamics is the study of relationships between heat and other forms of energy. Mostly work is the one we're really concerned about. And it's only concerned with differences between equilibrium states. Those are the endpoints of the processes. Heat transfer goes beyond thermodynamics to look at non-equilibrium conditions when there's temperature differences that result in heat transfer. So it must obey the first and second laws of thermodynamics, but it also is based on other branches of science. We bring in physics and a bunch of other areas. From an engineering perspective, the key problem for heat transfer analysis is to determine the rate of energy transfer, how quickly energy moves, or the heat flow, if you will. And then once we've done that, we can start estimating things like feasibility, what kind of equipment is necessary, and how much it's going to cost to accomplish a task. Another thing to remember as engineers, it's very difficult to describe physical phenomena exactly. So as engineers, we're going to use assumptions and idealizations to simplify our equations to the point where we can make engineering predictions relatively quickly. The basic idea here is we don't need a perfect representation of what's happening in order to make a decision. We need a representation that's good enough for us to, say, compare two options, or to develop a design with a particular safety factor, or something like that. So just enough to make engineering decisions. And we start that by looking at the first law of thermodynamics. Now, the first law of thermodynamics is often called the conservation of energy, but the energy that's conserved is the total energy. Okay, it includes the mechanical energy, the thermal energy, the stored energy, things like chemical and nuclear energy that are not typically seen in equations for the first law. So it's not totally correct to say this equation represents conservation of energy, because there are types of energy that must be conserved that are not included. So we'll call this the first law of thermodynamics. So the total energy here, I said, includes mechanical, thermal, and stored energy. So mechanical energy is typically things like kinetic energy or potential energy. Usually, heat transfer problems don't need to account for these because they're very small compared to the thermal energy. So, for most practical problems, we can replace the E, total energy, with U, internal energy. Internal energy is often also called thermal energy. It's the U, and we can break this up into two components. The first is sensible heat. Sensible heat is due to changes in temperature. So when the temperature of an object rises, it has more energy. And the amount of the energy change is described by the specific heat capacity times the temperature difference, or the change in temperature. We also have latent heat. Latent heat is due to phase change. For instance, when something goes from a solid to a liquid and melts, the temperature of the substance doesn't necessarily change, but it does have more energy after it melts, and that's the latent heat. It's an increase in thermal energy that's not associated with a change in temperature, but rather with a phase change. And we also talked about stored energy. So in this case, we're looking at things like chemical energy and nuclear energy, which you can see are not explicitly accounted for in our equation, which is why we're calling it the first law rather than conservation of energy. So when we look at the first law, there are two basic approaches, and the first is called the control mass approach. In the control mass approach, we're looking at a lump of a substance, and we're always going to be looking at the same lump of the same substance. So we might be looking at a solid sphere, or a solid brick, or a particular volume of fluid, and we're going to follow that mass of fluid as it moves through a system. The benefit to the control mass approach is that no fluid can cross the boundary of our control mass. So the velocity dot area term in the surface integral is 0, since there's no flow across that surface. And then we can integrate this over time to come up with the control mass version of the first law, which is total energy minus total work equals total change in internal energy. The second approach is the control volume approach. As we've discussed through fluid mechanics and so on, we can actually convert the surface integral into a sum over all of the inlets and outlets. And then the next thing we're going to do is make an assumption that the flow is uniform. So this allows us to remove the velocity, and if we assume incompressible flow, we can remove the density from the integral. So occasionally we also assume steady state. If we assume steady state, then the time derivative can be assumed to be 0. And then we need to make some definitions. So the first definition is the mass flow rate. So we already assumed that velocity is uniform, so now density times the uniform velocity times the area gives us the mass flow rate. We're also going to define the enthalpy. So the enthalpy is defined as internal energy plus this quantity, pressure over density. Pressure over density measures the potential of a substance to do work. Basically, it's been compressed, and because it's been compressed, it can expand, and when it expands, it can do work. So the change in enthalpy then is also described by a specific heat capacity, but in this case, we're looking at C sub P, the specific heat capacity at constant pressure, where before we were looking at C sub V, the specific heat capacity at constant volume. So with these definitions, we can actually simplify this equation even further, and we can convert the integral into a sum over all of the inlets and outlets, and then we can reduce it to the summation of mass flow rate times enthalpy. I want to make a note here. In the textbook, they use the variable H for enthalpy, and that's what you typically see in thermodynamics textbooks as well. However, in this class, we're going to use I for enthalpy instead. The reason I want to do that is because we're going to use H for heat transfer coefficient throughout most of the class, and I want to avoid confusion between enthalpy and heat transfer coefficient. So enthalpy will be I, heat transfer coefficient will be H. Once we've simplified this a little bit, we could actually integrate over time, and we would end up with total energy minus total work equals change in internal energy plus the total energy in and out with the flow. We could also assume steady state, in which case we would be able to simplify this equation to rate of heat input minus rate of work done equals energy in minus energy out with the flow. So then we can relate energy input, power, work input or output, and the change in the energy of a fluid as it flows through a control volume. So remember, the sign on the mass flow rate is determined by the direction of the dot product. Okay. So in the first law, there were two big quantities. The first was heat, the second is work. So heat typically gets divided up into energy generation and energy transfer. Energy generation is due to the conversion of some other type of energy into thermal energy. So we can have chemical reactions like combustion that could be either exothermic, which produces energy, or endothermic, which absorb energy in order for the chemical reaction to occur. We can also have nuclear reactions, decay, fission, etc., or electrical energy, resistance heating, friction can generate heat energy. Typically, we express it on a per unit volume basis. So we can do watts per cubic meter, or we can express it per unit mass, watts per kilogram of mass in our system. Energy transfer is a surface phenomena. So inflow and outflow of energy from the system occur at a surface. We can talk about work interactions, which is what we're going to discuss next. There's mass transfer across the control surface. This is our what we call advection term. That's what we talked about in fluid mechanics. And then we also have heat transfer, which is the rest of this course. So the other term was the work term. Work done by a fluid is positive. Work done on a fluid is negative. We call that the sign convention. And there's many categories of work. We can talk about viscous work. Most of the time that's going to be assumed to be zero in this class. We also have shaft work, which is the work done by pumps or on a turbine. And then there's other forms of work, which is kind of a catch-all to just account for whatever forms of work we might have in our particular problem. Pistons, things like that. That's not really the focus of this course. That's what you'll learn about in a thermodynamics course or a power plant systems course. They're more focused on work. So for the most part, we're not going to spend a lot of time on work in this class, since we're focused more on the heat transfer aspect of the first law. So there are some important simplifications. If we assume that our system is steady state, we're not generating any energy. Our fluid is either an ideal gas or an incompressible liquid. We neglect our mechanical energy. We don't worry about work. And we only have one outlet and one inlet. So the fluid comes in at one spot, flows through the system, and leaves at one other spot, and that's it. Then we can actually simplify the first law to heat transfer equals mass flow times specific heat times change in temperature between the inlet and the outlet. So this form can be useful to relate the energy absorbed by a fluid to its temperature increase. Now, when we apply the first law, there are steps we have to do. The first is to identify our control volume and control surfaces. And in this instance, it might be really helpful to draw a schematic of the system and show, here's my control surface, here's my control volume. Then we need to decide, are we looking at an interval or a rate? So if it's an interval, we'll be looking at energy in joules or a BTU or something like that. And if it's a rate equation, we'll be interested in watts or horsepower or something like that. So which interval or which type of the equation are you going to use? And then the next step is going to be to identify all of the energy-related terms. Where is energy being transported? Is there flow that's carrying energy? Is there conduction or convection or something like that? And then indicate all of this stuff on your drawing, so everybody can see the terms that you were accounting for and everything like that. And then you write the correct form of the first law. And once you've done that, you'll get into what we start doing in the rest of the course, which is substitute the equations for conduction, convection, etc. And once you've substituted everything, then you can solve for whatever it is you're looking for, your unknown quantity. The last thing I want to talk about is the second law of thermodynamics. You might have heard this, this idea that entropy in the universe is always increasing. The second law determines the direction and allowability of a process. There are many ways to express the second law, but it basically comes down to certain practical limitations that we have to address as engineers. Heat flow has to move from a hot region at high temperature to a cold region at lower temperature. Heat never moves from a cold location to a hot location. Friction has to act against motion. I mean, if friction acted with motion, then the friction force would cause objects to speed up, and we know that that doesn't make any sense. It violates the second law of thermodynamics. So friction always has to act against motion. So these are just some practical effects of the second law. You'll learn more about second law in a thermodynamics course or a power systems course.